Big news! The Large Hadron Collider is being switched off. That sounds scary, especially if you've heard the old rumor that this machine would create a black hole and destroy Earth. Wait, is it finally happening? Is that why they're shutting it down? So, the Large Hadron Collider, or just the LHC, is the biggest science machine ever built. It's a giant ring-shaped tunnel deep underground near Geneva, where scientists smash tiny particles together at crazy speeds. They do it to copy, for a split second, what the universe was like right after the Big Bang. By recreating those conditions, the experiment could reveal some of the universe's deepest secrets. And now, this iconic machine is shutting down. It won't be permanent though. They have to power it down so the team can do major engineering work and install some big upgrades. And that process will take around 5 years. Scientists guarantee the LHC isn't shutting down because of a problem. If anything, the machine is still working great and gathering massive amounts of data. But don't get it twisted. The famous atom smasher isn't going to run forever. It will probably retire around 2041. And after that, it may be replaced by a massive machine called the Future Circular Collider, or FCC. But before we explain what's coming next, let's talk about how the Large Hadron Collider actually works. This is the world's most powerful particle accelerator. Think of it as a metal ring buried deep underground right under the border between France and Switzerland. And it's huge, around 17 miles around. It was built to answer a very old question. What is everything made of? Basically, the LHC lets scientists recreate conditions similar to those right after the universe began. Inside this ring, scientists send tiny particles racing around at almost the speed of light. These particles are like microscopic race cars, guided by powerful magnets that bend and steer them around the loop again and again. As they go faster and faster, they carry enormous energy, even though they're unbelievably small. At certain points around the ring, scientists smash these particles together head-on. When they collide, they break apart and turn into showers of other particles. Scientists record everything they can about those conditions and basically hope it helps answer some huge questions about the origin and structure of reality itself. This $10 billion project began in 1989 and became operational in 2008. Then, in 2012, it made a major breakthrough by discovering the Higgs boson. This is a fundamental particle associated with the Higgs field, a theory first proposed back in the 1960s. To understand it, let's use a rock and a light. Both are made of particles. Now put them on a scale. The rock shows up right away. It has mass, so it has weight. But you can't really weigh light on a scale because it doesn't weigh anything. What I mean is that some particles are massless, or close to it. Take photons, for example. They carry the electromagnetic force and have no mass at all. Same goes for gluons, the particles that help hold matter together. But plenty of other particles do have mass, and for a long time, the big question was, where does that heaviness come from? This theory says there's something spread throughout the entire universe called the Higgs field. Some particles interact with it more than others. The more they bump into it, the more mass they end up with. Photons and gluons, on the other hand, don't interact with the Higgs field directly, and that is why they don't get mass from it. So, discovering the Higgs boson particle is basically the big clue that this field is real. But here's the thing. Elementary particles get their mass from the Higgs field, but nobody really knows why different particles end up with such different masses. Actually, we don't even fully understand how Higgs bosons interact with each other. To help answer those questions and a bunch more, scientists need to upgrade the LHC. The plan is to shut it down now for the next 5 years to build the, drumroll please, high luminosity LHC. Basically, that means installing powerful new superconducting magnets that squeeze the proton beams and make them more intense. That should boost the number of collisions inside the machine by about 10 times. The detectors are getting upgrades too. so researchers can spot even subtler signals and catch hints of new physics hiding in those collisions. So the whole team is crossing their fingers that the upgrade will go as planned. Because with these changes, the LHC will be able to make more precise measurements of particles and how they interact. And that could reveal cracks in what we think we know about the universe. Now you can see why this machine makes some people nervous, right? Some worry it could destroy the world by creating mini black holes, strange matter, or even vacuum bubbles. Basically, doomsday scenarios. But experts say there's no real risk of that, or at least it's extremely unlikely. Either way, you don't have to worry about them turning it off. Nothing bad happens when the machine stops, and we know that because this isn't even the first time it's taken a vacation. The Large Hadron Collider has already gone through 2 major multi-year shutdowns for maintenance and upgrades. One happened back in 2013 and another in 2018, so the shutdown planned for 2026 will be the third one. In other words, yeah, these kinds of pauses are pretty standard, so there's really no reason to panic. Over the next few years, the team will be focused on getting the high luminosity LHC up and running. But at the same time, some much bigger and more controversial projects will also demand their attention. Like we mentioned earlier, the LHC won't last forever. At some point, it'll likely be replaced by something even bigger, the Future Circular Collider, or FCC. We're talking about a brand new circular tunnel with a circumference of about 56 miles, dug as deep as about 1,300 feet underground, and it would be built in 2 stages. The first stage, starting in the late 2040s, would collide electrons with positrons, which are basically their antimatter twins. Then, sometime in the 2070s, that machine would be taken out to make room for a new collider that smashes protons at about 7 times the energy of the LHC. Building something this huge would cost a ridiculous amount of money, sure. The estimate is around $18 billion, and that's just for the first phase. But the team believes spending that much money will be worth it. They say this new machine is necessary to answer even deeper questions, like what role the Higgs field played in the evolution of the universe. Or maybe it can help explain the nature of dark matter. And what about the imbalance between matter and antimatter? To get answers like these, scientists would need to create conditions that point to the existence of new, much heavier particles. Particles that the current Large Hadron Collider simply isn't powerful enough to produce. The Future Circular Collider still has some big technical challenges ahead, but a lot of groundwork has already been done to shape the project. CERN, the European Organization for Nuclear Research that runs these experiments, has already completed an extensive feasibility study. The report confirmed the project is technically doable, and it laid out the next steps towards a detailed design. Right now, this study is being reviewed by the CERN Council, and around 2028, they could decide whether to move forward with the FCC. So for now, the LHC is shutting down for its next big upgrade, and someday it will shut down for good. Not because it failed, but to make room for something even bigger and more powerful. If the next machine gets built, maybe it won't just smash particles. Maybe it'll push us a little closer to the biggest answers of all. Like, what are we? And where do we come from? And yeah, that's pretty exciting.
Do you know that our planet has scars? One of them is located in North America. This scar can tell us many cool things about the history of Earth, but the most interesting thing is that it could change the appearance of our continents and break our world. But for some reason, this scar hasn't done it yet. And that's not even the most interesting part. The coolest thing about this scar is that it might hold a giant source of clean, cheap energy. So let's go to Kansas to find out what it is. So, 1.1 billion years ago, a giant rift formed in the crust of our planet on the territory of the modern U.S. Midwest. It's called Broken Heart. This giant crevice is filled with solidified magma, and from afar, it looks like a real scar. But how did it show up? Broken Heart was an ancient rift valley, a huge geological fault forming elongated hollows in the Earth's crust. It occurred because tectonic plates had moved apart. It's like the details of a jigsaw puzzle that suddenly started to separate. At that moment, thousands and even millions of tons of magma spilled out from the depths of our planet. That event looked like a real apocalypse, lasting about 100,000 years. But then it stopped, and scientists don't know why. If the rifting process had lasted longer, then most likely the continent of North America would look different today, or it wouldn't even exist at all. Right now, this fault looks like a giant horseshoe that stretches from Kansas north to Lake Superior and south to Michigan. But some studies indicate that the fault may be larger and extend even further south, and the width of the fault might equal the width of the Red Sea. After the rifting stopped, the entire valley got covered with hills and trees. The fault itself is covered with a thick layer of sedimentary rocks, so it's quite difficult to track. The most noticeable parts of the rift are in the Lake Superior area. Now everything looks calm and beautiful, but in the past, there were fountains and rivers of lava, earthquakes, a boiling pot on a planetary scale. All that remains of it are deposits of basalt, a dark, dense rock that forms from cooled lava. There was so much basalt that its weight pushed the valley deeper and deeper into the Earth's crust. Even when the eruptions and rifting stopped, the valley continued to sink because of the huge mass of this sediment. Then, massive sections of the Earth's crust on both sides of the valley began to contract, and the pieces of the puzzle slowly started to come together. This led to a large-scale ejection of volcanic material upward, and along with basalt, deposits of copper rock appeared in the valley. People mined this copper for about 8,000 years until the end of the 20th century. The copper mines were eventually shut down, but now it seems the industry is making a comeback. However, Broken Heart is not interesting to people just because of its copper reserves. It holds something more valuable and useful for our civilization. Scientists believe that this valley hides massive reserves of hydrogen, and this substance can help us switch to a cleaner, cheaper, and more efficient energy source. If hydrogen fuel becomes widely available, everyone will switch to it, leaving behind the costly, noisy, and polluting process of oil production. Now, I'll bet hydrogen is a remarkably familiar word to you. It doesn't sound like the discovery of the century, and people have been using it for a long time. On one hand, you're right, but not quite. 90% of the hydrogen produced by humans is used as a raw material for the chemical industry. Hydrogen is used to produce ammonia for fertilizers, methanol for fuel and solvents, and to purify crude oil. Manufacturers of glass, cement, steel, and other metals are considering using hydrogen at their factories for more efficient production. Hydrogen can become an alternative to fossil fuels, that is, oil and gasoline produced from them. Cars, ships, trains, airplanes, and power plants, all of these may switch to hydrogen soon. In this case, production can become cheaper and better for nature, but this will work only if we find open sources of hydrogen. You see, about 95% of the hydrogen we use is produced from fossil fuels. We gasify coal, oxidize hydrocarbons, and extract hydrogen from methane. All of these production methods require energy. But the worst part is that they lead to large emissions of carbon dioxide into the atmosphere. But what if we find sources of pure hydrogen that don't require processing? Then we'll save energy for its production and make the planet cleaner. But where can we find such sources? Scientists say that there are many of them all over the planet, and one of the largest is located in the Rift Valley in the U.S. Midwest. But what's the problem with going and mining it? Well, it's not that simple. To extract pure hydrogen, you need 3 conditions. The first is the source of hydrogen itself, which is quite logical. The second is reservoir rocks, that is, natural containers where this hydrogen is stored. And the third is natural seals, which prevent the gas from escaping. In other words, these seals work like a cap on a bottle. They don't allow the substance to escape. So in general, it's necessary to find where hydrogen is released, where it accumulates, and where it's stored. When these conditions are met, natural resource extraction companies can start working. But how does hydrogen appear altogether? Well, let's go over the basics of chemistry. Hydrogen and oxygen compounds form water. This means you need to split the water into hydrogen and oxygen. This process often occurs in nature. There are many places all over the planet where this happens. Scientists are confident that at least 30 U.S. states have hydrogen reservoirs. And if people detect them, we will accelerate the energy transition to safer and more efficient fuels. Thousands of cars drive around using gasoline. Many of you know the smell of exhaust fumes, that thick polluted air that's hard to breathe. What about electric cars? They must be improving the situation, right? Well, here's another problem. Producing batteries for these vehicles harms nature. The materials used to make batteries are lithium, cobalt, and nickel. Their extraction involves a large release of toxic materials, not only into the air but also into the water. Transporting these batteries also creates a large carbon footprint. Producing a single electric car emits about 4 tons of carbon dioxide. To make up for that, the owner needs to drive it for at least 8 years. That's how long it takes to offset the emissions a regular car would produce. What about reliability and convenience? What will you do if the battery runs out during the trip and there are no charging stations nearby? This problem will be solved in the future with the growing popularity of electric cars. Now, scientists believe that over the past billion years, the Earth's crust has split enough water into hydrogen and oxygen. Our planet keeps this gas in the ground, waiting for us to start using it. According to calculations, even considering all the technologies and production capacities of our civilization, the reserves of hydrogen in the bowels of the planet are enough to supply us with energy for 170,000 years. That's why the giant rift in Kansas attracts scientists from all over the world. Huge quantities of basalt and other rocks can react with water to release hydrogen. And now scientists are looking for places where this material accumulates and is stored.
While you're watching this video, pieces of continents are slowly breaking off from below and are pulled down into the oceanic mantle, a hot, mostly solid layer that moves slowly under the seafloor. As soon as these fragments reach the mantle, they can trigger volcanic eruptions in parts of the ocean where there are no volcanoes. Plus, when continents break apart, it happens not only at the surface, but also deep down. But more on that later. This process can continue for tens of millions of years. The new study shows that Earth's insides are even more dynamic than we thought. It also explains why many volcanic islands, including Christmas Island in the Northeast Indian Ocean, contain unusually high levels of certain chemical elements. The thing is, these elements are normally only found in continental crust. Well, scientists did suspect that these elements showed up because some powerful forces deep inside the Earth took old, recycled pieces of rock and mixed them into the mantle. This process works a bit like when you mix together ingredients for cake batter. But before, researchers believed those elements came from 2 main sources: sediment that sank into the mantle as oceanic plates got pushed down, or from mantle plumes. Those are columns of hot rock rising up from deep inside Earth. However, these explanations don't fit all observations. In some volcanic areas, there's almost no sign that the crust has been recycled. In other places, the mantle seems to cool and too close to the surface to be affected by the rising hot rock. Scientists used to wonder how this could happen. Now we know that some of the material in those regions comes from pieces of continents that sink deep into the mantle, and these pieces affect the volcanoes that form above. The new study also suggests a curious idea. Continents don't just break apart at the surface, they peel away from below too. And this can happen over much greater distances than scientists thought before. Researchers used simulations to figure out how continents and the mantle behaved when stretched by tectonic forces. Their work is built on earlier research showing that when continents split deep, powerful forces inside our planet create a mantle wave. This wave moves along the base of the continent at depths of about 90 to 125 miles. The wave moves extremely slowly, about a millionth of the speed of a snail, and gradually strips material from the roots of the continents. These peeled-off fragments are then carried sideways, sometimes more than 620 miles, into the oceanic mantle. Once there, they can trigger volcanic eruptions in the ocean for tens of millions of years. The research also shows that the mantle continues to feel effects of continental breakup long after the continents themselves have separated. Even after a new ocean basin forms, the mantle keeps moving, reorganizing and transporting enriched material far from where it originally came. To make this conclusion, researchers studied geochemical data from different parts of the Earth, including the Indian Ocean Seamount Province. That's a chain of volcanic formations that appeared after the supercontinent Gondwana had broken apart over 100 million years ago. Their computer models and chemical tests showed that right after the supercontinent Gondwana broke apart, a lot of magma with unusual chemicals pushed up to the surface. Over millions of years, this chemical signature slowly faded as less material came up from under the continent. The most unexpected discovery is that this happened without any help from those deep, hot columns of rock scientists used to think were needed. Now, to get an even clearer picture, let's sneak a peek into our planet's insides. Earth is about 4.6 billion years old. It was born from a huge cloud of dust and gas that slowly cooled, shrank, and hardened into the planet we know today. As it cooled, heavy metals like iron and nickel sank to the center, and lighter, rocky materials floated upward. This created the Earth's layered structure, with each layer having its own unique properties. The crust is like Earth's skin. It's our planet's outermost layer, made of solid rock. It's broken into huge pieces called tectonic plates that slowly drift over time. There are two kinds of crust: oceanic crust and continental crust. The oceanic crust is about 4 to 6 miles thick. It's covered with a thin layer of sediments like sand, clay, and shells. Below that are dense rocks like basalt, rich in magnesium. As for the continental crust, it's thicker than oceanic crust and is located under continents. It's made of lighter rocks than oceanic crust. Beneath the crust is the mantle. It makes up more than 75% of Earth's volume. The top of the mantle is pretty rigid, but deeper down it becomes soft and partially molten, which allows it to flow slowly. This flow is what moves the tectonic plates. At the center of the Earth lies the core. It's made mostly of iron and nickel and has two distinct layers, the outer core and the inner core. The outer core is a liquid layer of iron and nickel. It's insanely hot, up to 10,800 degrees Fahrenheit, as hot as the surface of the sun. The outer core also generates Earth's magnetic field, which protects us from harmful solar radiation. The inner core is solid because of the crushing pressure inside the planet. It's also made of iron and nickel. Now, the Earth's outer shell, called the lithosphere, is made up of the crust and the uppermost part of the mantle. It's broken into large pieces, called tectonic plates. There are a few super large plates and many smaller ones. 6 of the major plates are named after the continents they carry, like the North American, African, and Antarctic plates. But even those smaller plates play an important role. For example, the tiny Juan de Fuca plate is responsible for many of the volcanoes in the Pacific Northwest of the United States. The plates are moving like a jumble of old conveyor belts. They move very slowly, about 1 to 2 inches per year. But over millions of years, this movement shapes the face of our planet. Most earthquakes, volcanoes, and mountain building happen where plates meet, pull apart, or slide past each other. There are 3 main types of plate boundaries: convergent, when plates move toward each other; divergent, when plates move apart. And transform. That's when plates slide sideways past each other. When tectonic plates collide, the crust crumples and buckles, forming mountain ranges. About 55 million years ago, India crashed into Asia, slowly creating the Himalayas, the tallest mountains on Earth. The collision continues today, so the mountains are still rising. Mount Everest, the highest point on Earth, may even grow a tiny bit taller over time. At some convergent boundaries, an oceanic plate dives under a land plate in a process called subduction. The land above lifts up, forming mountains, and the sinking plate melts and triggers volcanic eruptions. This is how some mountains in the Andes of South America were formed. When two oceanic plates collide, one usually slides beneath the other, creating deep ocean trenches, like the Mariana Trench in the North Pacific, the deepest point on Earth. These collisions can also form underwater volcanoes that eventually rise above the ocean and turn into island chains, such as Japan. At divergent boundaries, tectonic plates move away from each other. In the oceans, magma from deep in the mantle rises to fill the gap. This creates underwater mountains and volcanoes along the seam. This process renews the ocean floor and slowly widens the ocean basins. By the way, a single mid-ocean ridge system connects all the world's oceans, making it the longest mountain range on Earth. On land, when plates pull apart, they form giant valleys, such as the Great Rift Valley in Africa. If this stretching continues over millions of years, East Africa could split off to become a new landmass. One famous example of transform boundaries is the San Andreas Fault in California. Unlike convergent or divergent boundaries, transform boundaries usually don't create mountains or oceans, but the grinding motion can cause powerful earthquakes, such as the 1906 earthquake that destroyed much of San Francisco.
Oh man, the sun did it again! It just blasted a huge cloud of plasma into space. This time, it was one of the fastest and most powerful eruptions of this solar cycle. It was so strong that the shockwave hit Venus, our next-door neighbor. That's when scientists got worried and started asking a scary question. Could Earth be next? Well, let's just cut to the chase. If your GPS and internet have been working fine over the last few weeks, and your city hasn't had any big blackouts lately, you already know the answer. No, that powerful blast didn't hit Earth. Or at least we didn't feel any real effects from it, because this event happened in October 21, 2025, and if our planet had been in its path, we would have felt the effects only a few days after that date. You see, we're talking about coronal mass ejections, or CMEs. From time to time, the sun throws a giant cloud of superhot plasma into space, straight from its outer layer, the corona. Think of plasma as a superheated gas. It's what the sun is made of, and it's full of tiny charged particles, positive ions and negative electrons. These outbursts happen because the sun's magnetic field is always moving and twisting. Sometimes the magnetic lines get tangled up, then suddenly snap and reset. This process is known as a magnetic reconnection. And when that happens, boom, the sun launches a CME. A single coronal mass ejection can throw billions of tons of material into the solar system in one shot, and it can create a shock wave. That shock wave can speed up charged particles, which raises the chance of a radiation storm. And if a planet is in the way, yeah, that can be trouble. The tricky part is that CMEs are pretty unpredictable. They can blast out in different directions, and they don't all move at the same speed. The fastest ones race through space at millions of miles per hour. If one is aimed at Earth, it can get here in as little as 15 hours. Slowest ones can take days to get here, but even then, it's usually somewhere between 1 and 5 days. It's not like months. Since this big blast happened a while ago, it's safe to say that, well, we're safe. And honestly, even if it had hit Earth, we'd probably be safe anyway. Sure, a strong CME can mess with satellites, disrupt radio and internet signals, and even knock out power grids for a while. but it's not the kind of thing that ends the world or wipes out humanity. So take a breath. Even a really powerful solar eruption isn't going to destroy Earth. Unfortunately, we can't say the same thing about Venus. CMEs hitting our neighboring planet are actually one of the reasons Venus can't support life, at least not what we consider life. But don't worry, we'll get to that part later. First, let's dive into this recent solar outburst and what made it so extreme. This one came from the far side of the Sun, the side we can't see from Earth, and it came from an especially active sunspot area called 4246. This is a new, huge, messy sunspot that's been responsible for the latest round of solar storms headed our way. The big blast happened right after that region rotated past the Sun's western edge, so it was out of view from Earth and from most weather satellites. Thankfully, the event was caught by an instrument on a NOAA satellite called CERN. Think of it like a special camera designed to spot big solar blasts even when they happen on the far side of the Sun. That's why it's strategically placed so high above Earth, and it orbits about 22,000 miles over the equator. The CERN manages to capture those images by blocking the Sun's blinding surface, so it can see the faint glow around it and track huge plasma clouds as they spread out into space. Now, let's talk about speed. NASA estimates that the CME in October was moving at about 820 miles per second. But the first radio signal suggested it might have been even faster, close to 1,537 miles per second. Trust me, that's crazy fast for a coronal mass ejection. To put that in perspective, only a handful of blasts in modern history have been quicker. One famous example happened in 2017 during an X-class flare rated around X8. So according to NASA, X-class means the strongest kind of solar flare. The number tells you how strong it is. An X1 is the baseline, an X2 is twice as strong, an X3 is 3 times as strong, and so on. So yeah, an X8 flare is something huge. Back on Earth, that 2017 event did mess a bit with high-frequency radio signals for a while. But for us, that was pretty much it. Mars was a different story. When the same event hit the red planet, it heated the upper atmosphere in an uneven way. In the hottest areas, scientists saw the top 2 layers, the thermosphere and the ionosphere, start interacting more than usual because of the blast. And that had a real effect. Oxygen began escaping into space much faster than normal. In other words, that brief event made Mars lose part of its atmosphere at a higher rate. Now, when we talk about this recent burst, the story is kind of similar, but with a twist. This time, Mars wasn't the main target, Venus was. The planet was sitting right in the path of the solar burst. So when the blast hit, Venus got slammed with a storm of charged particles. Now you might be wondering, why is it a bigger problem when a solar eruption hits planets like Venus or Mars, but not as big of a deal for us here on Earth? Well, it's because of Earth's magnetic field. So big blasts from the Sun can mess with the atmosphere around a planet. But on Earth, a lot of that impact gets blocked by a natural magnetic bubble called the magnetosphere. Good thing, huh? Here's how it works. A wave of plasma comes from the Sun and slams into the magnetosphere, the region around Earth controlled by our magnetic field. That magnetic field pushes most of the charged particles away, kind of like a shield, but not all of them. Some particles still sneak through and crash into the upper atmosphere. When that happens, we can get geomagnetic storms. These storms create amazing auroras. They can also mess with satellites and communication networks, like we talked about earlier. But some planets, like Venus, don't have a strong magnetic field like Earth does, and that can be bad news. Because when a CME wave reaches Venus, the charged particles crash straight into the atmosphere and, over time, slowly peel parts of it away. Now here's a real example. On December 19, 2006, the Sun released a small, slow CME. Even though it wasn't moving fast, it was still strong enough to do damage. About 4 days later, it reached Venus and ripped away a large amount of oxygen from the planet's atmosphere, sending it off into space for good or bad. And this is actually one of the big reasons why planets like Venus are uninhabitable. Without a strong magnetic field, CMAs can slowly strip away their atmosphere, blast the surface with dangerous radiation, and create brutal space weather conditions. Venus is a perfect example. It is the hottest planet in our solar system, being 100 times hotter than Earth. Its atmosphere is insanely thick, and the pressure over there is insane, so much so that the longest any spacecraft has survived on its surface before being crushed is a little over 2 hours. Scientists think that getting hit by solar eruptions without a proper magnetosphere to protect it helped push Venus toward this extreme world. And by studying what happens to planets like Venus, we can learn something bigger: how important a magnetic shield might be for life on other worlds we find outside our solar system.
It's one small step for man, giant leap for mankind.
In the late 1950s, everyone was captivated by space exploration. But there was a group of rebels who wondered not what's out there, but what's down there. This team called themselves the American Miscellaneous Society. Yes, that's their real name. And they started one of the biggest projects ever, Project Mohole. Joyful and determined, they had no idea what a nightmare they started. First, let's understand what the project was about. You probably know that Earth is like a giant onion. If you cut it in half, you'd see it's made of layers. Each one is different from the next. The crust is what we all stand on. It's incredibly thin, like the skin of an apple. It's made of tectonic plates, almost like puzzle pieces, and they float on the layer beneath. That layer is the mantle. It's mostly solid, made of rock, but these rocks flow and move very slowly, just a little bit over thousands of years. They're also incredibly hot, thousands of degrees Fahrenheit, so it's a bunch of scorching stones moving around like caramel syrup. And when the mantle moves, the tectonic plates above move as well. Usually, this movement is slow and harmless. We don't even notice it. But sometimes they can bump into each other, get stuck, and so on. And when they do, they send such horrifying vibrations through the ground that they're hard not to notice. These vibrations are called seismic waves. In 1909, a Croatian scientist, Andrija Mohorovičić, noticed something weird. Turns out, at a certain depth, seismic waves suddenly speed up. He didn't yet realize that he stumbled upon a boundary between the crust and the mantle. It became known as the Mohole boundary. Now, try to guess what the Project Mohole guys decided to do. It was during a meeting of the National Science Foundation. Everyone was discussing current scientific progress. Suddenly, Walter Munk, a geophysicist and oceanographer, casually threw out a take that shocked the room. Why not drill all the way down to the mantle? His idea was outrageous. Drill through the ocean floor, deep into the planet's skin, reach the Mohole, and see what it's all about. Never mind the fact that the ocean is crazy deep with crushing temperatures and violent currents. Super bold, but not entirely out of nowhere. If we start from the ocean floor, the Mohole lies just about 3 to 6 miles below it. It's much easier than starting from land. That would require digging from 10 to 60 miles deep. That made the oceans the best bet for reaching it. Munk wasn't the only one. Harry Hess, one of his colleagues, was just as excited about the time. At the time, people didn't know much about plate tectonics. Hess was one of the founders of that theory, believing that the world is made up of giant moving plates. To him, it was great. Drilling to the mantle would give him evidence to prove that theory. They became a team and found more like-minded scientists. They combined the most brilliant minds in earth science: Roger Revelle, Maurice Ewing, and Arthur Maxwell. They called themselves Miscellaneous because there were all sorts of scientists in the team. Poor guys didn't know that their playful name would later come back to haunt them. But the NSF was dumbfounded by their idea at first and rejected it, because duh, it would be a nightmare to pull off. So our team secured $50,000 just to make a plan. Then they presented the official banner. Luckily, science was on the rise, and there were rumors about other countries trying their own deep drilling projects. So the AMS got the green light this time. The plan consisted of 3 phases. Phase 1. Do a drilling test. Check how things are going. Phase 2. Build an intermediate drilling vessel. Phase 3. Keep going until they reach the Mohole. And they got a funding of a whopping $2.5 million. And finally, in March and April 1961, the project finally began. Phase 1 took place off the coast of Guadalupe Island, Mexico. They used a converted barge called CUS-1 and some insane brain moves to make it work. Originally, CUS-1 was made for drilling oil offshore. It was one of the best things we had for drilling in deep water. But a catch was that it could only go a few hundred feet down. And remember, we need at least 3 miles. The team had to come up with something revolutionary: dynamic positioning. It's a tech that allowed the ship to stay perfectly still in the middle of the ocean, even without an anchor. It worked like this. They dropped 6 buoys into the water, forming a circle around the ship. These buoys sent underwater echoes to help the ship understand where it's located. Using motors and a joystick, the crew could keep CUS-1 right in the center of the circle. And surprisingly, they started making progress. Even though ocean drilling is incredibly hard, they drilled through thick layers of sediment and reached an astonishing 600 feet below the seafloor, about 2 Statues of Liberty. And the seafloor itself was almost 12,000 feet deep. This was just the beginning. Deep down, they stumbled upon tons of basalt, a type of volcanic rock. It doesn't surprise us now, but for that time, this achievement was groundbreaking. Turns out they got through Miocene-age sediments, rocks formed millions of years ago. This discovery told us so much about the history of our planet. Now the entire world held its breath. Even the famous writer John Steinbeck, the author of East of Eden and The Grapes of Wrath, got caught up in the excitement. He joined the project and wrote a dramatic article about it for Life magazine. He wrote that we knew less about the ocean floor than we knew about the moon. That line stuck. The biggest surprise was that President John F. Kennedy sent a telegram congratulating the team. It's like the space race turned into inner space, and for a brief moment, it looked like they just might do it. But years later, Walter Munk said that the very success of Phase 1 doomed the project. The early triumph raised expectations sky high. From the start, the miscellaneousness of this society led to tons of disagreements, logistical hurdles, and the costs just kept rising. When the NSF realized just how successful the project was, they took over in 1961. The original society became just an advisor, and this completely screwed things up. One of the scientists said that it was a lengthy and unattractive trail of bickering, bitterness, and short-sightedness. They wouldn't even decide what exactly they wanted to do and whether they even want to reach the Mohole. After that, the project found the new contractor company, Brown and Root, but it was a political decision, not a scientific one. Brown and Root had no experience in deep-sea drilling at all. Poor scientists had to suffer because this company didn't understand the project's goals and how hard it is. Some scientists even quit because of how annoying that was. As a result, when they calculated how much it would actually take to reach the Mohole, it turned out to be about $1 billion by today's standards. This shocked absolutely everyone. The public was mocking them, which didn't help at all. Some articles called it Project No Hole and gave titles like How NSF Got Lost in Mohole. The final blow happened in '66. The project's most loyal supporter, Albert Thomas, passed away. Plus, the situation in Vietnam was escalating. As a result, the project was stopped after eating up tens of millions of dollars. What's even worse, this giant, impossible idea took the funding from smaller and achievable things. But it wasn't entirely for nothing. Project Mohole pioneered a new deep-sea drilling technique, which is now standard. They also inspired many new, similar, smaller ideas. And science just kept going since then. In May 2023, scientists finally achieved this dream. They actually pulled up rocks not even from the Mohole boundary, but from the mantle itself. They got them from the bottom of the Atlantic Ocean. So maybe one day we'll be able to drill all the way down there.
Guess what? A huge ocean might be hidden deep beneath us, about 250 to 400 miles down, and it's bigger than any ocean on Earth's surface. Scientists were listening to earthquakes deep within our planet and noticed how these shakes slowed down when passing through certain parts of the mantle. This suggested that water was there. Models and experiments led them to uncover the underground ocean. But this ocean isn't like the typical water you imagine. It's a lot crazier. The mantle is a thick layer between the Earth's crust and core. It consists of the upper mantle, the lower mantle, and a mysterious layer between them called the transition zone. In the upper layer, we can often find a fascinating material called olivine, which got its name from a pretty greenish color. Olivine doesn't care about high temperatures and thrives in lava comfortably. It not only thrives, but it even makes up 50% of the entire upper mantle. We can find this stuff on Earth thanks to volcanoes. When volcanoes spew their magma out, all the minerals in it make their way to the surface. As magma cools and solidifies, it forms igneous rocks, and the minerals start to crystallize. Olivine is one of the first minerals to crystallize, and since there's so much of it in magma, it forms lots of crystals. Sometimes they're small, but sometimes they grow large and become very noticeable. We collect these large gemstones and use them to make pretty accessories and for other purposes, such as casting metals. But as we dive deeper within the Earth, about 250 miles down, things get strange for olivine. We enter the mysterious transition zone. The pressures get way higher, and the temperatures rise significantly. Here, olivine transforms into beautiful rock called wadsleyite and ringwoodite. Just like with olivine, we sometimes find them thanks to volcanic activity. Both are blue-green with a beautiful glassy appearance. Unfortunately, they're exceedingly rare and small, so you can't make accessories out of them. They're usually studied in labs. But they can do something that olivine can't. Thanks to their structure, they can act like a sponge, soaking up water. Now, this doesn't mean that they're literally wet. Rather, wadsleyite and ringwoodite can store water components, hydrogen and oxygen, within their structure. Usually, up to about 3% of them are water particles. These two little guys play an immense role in our planet's geology. They influence how the Earth's mantle conducts electricity as well as its viscosity, or how well it flows. This affects mantle convection, plate tectonics, and even volcanic activity. Without these tiny crystals, our planet would be completely different. The world could be mostly underwater, with just a few mountaintops visible. They also help us better understand how water works in general. So the transition zone is special because it's hydrated. Here we come to the recent discovery, a massive underground water reservoir. Scientists try to understand how water behaves in this deep part of the Earth. They discovered that as water-rich ringwoodite moves even deeper into the Earth to the lower mantle, it can start to melt a bit. This means it can release a bit of water and then trap it somewhere underground instead of letting it move around freely. But this released water wouldn't really be in its liquid, solid, or gas forms. Instead, it would be chemically bound to the underground structures. So, it won't be an ocean in the traditional sense, but there might be a vast amount of water down there. This finding is super important because it changes the way we understand Earth's water cycle and resources. It turns out that water isn't just found on the surface, but also moves through hidden spaces deep inside the planet. Another fascinating thing we discovered about water is that it might exist in a mysterious fourth state of matter. Now, we're used to thinking of water in its three common states: solid, liquid, and gas. But under extreme pressure in tiny spaces, it can enter a mysterious fourth state known as tunneling. We discovered this strange behavior in the mineral called beryl. Within beryl, there are super small six-sided channels, just about 5 atoms across. Turns out these channels act like tiny cages that can trap individual water molecules, like wadsleyite and ringwoodite. In these conditions, the water molecules start showing behaviors that are closer not to classical physics, but to quantum physics. Quantum tunneling allows particles to exist in multiple places at once or pass through barriers they shouldn't be able to. Imagine a ball that somehow ends up on the other side of a hill without climbing over it. It just goes through the hill. Hydrogen atoms in beryl are like tiny balls. Typically, each ball would sit in one specific spot. However, in the experiment, these hydrogen atoms didn't stay still. Instead, they were found simultaneously in multiple spots. Together, they formed a pattern that looked like 2 wavy rings. It's like water molecules got smeared around in a ring shape. This is a state of water that we've never seen before. It reshapes our understanding of how water behaves under certain conditions, and it has huge implications for biology. All these discoveries have everyone rethinking where Earth's water really comes from. Water is essential for life as we know it. About 71% of Earth is drenched in water, and humans are mostly water too. When we figure out how it appears in space and on planets, it will give us clues about how to better search for extraterrestrial life. One theory says that when Earth was forming, the materials that clumped together to make the planet already included water, or at least the ingredients to make it. Earth formed about 4.5 billion years ago. Our planet slowly emerged thanks to gravity from dust, gas, and rocks that surrounded our newborn sun. This material gradually came together to form the planets of our solar system. However, the young inner solar system was a scorching place, too hot for any liquid water to survive. It would have simply vaporized and escaped into space. But it's possible that water was trapped inside the rocks that initially formed Earth. Some of the Earth's original building block contained much more hydrogen than all our oceans combined. It would also explain how water molecules got so deep underground. Then, volcanic activity could have later released the water stored deep within, sending it into the atmosphere as vapor. This vapor would eventually cool down, condense, and fall as rain, filling the young Earth with lakes and seas. Another idea is that after Earth was formed, water was brought here by wet space visitors like comets and asteroids crashing into the planet. Long ago, the inner solar system was a wild and chaotic place, much like Brightside. When the outer planets rearranged their orbits, this caused a ripple effect, which we now call the Late Heavy Bombardment. It sent a flurry of icy space rocks crashing through the inner solar system, many of which collided with Earth. For a while, scientists thought that this event and comets were a primary source of Earth's water. But then, we learned that comets have a different chemical makeup from the water on Earth. Then we looked at the asteroids. Their water closely resembles the water in Earth's oceans. Some of the samples even contained organic materials. There's also a chance some random planet helped us out. About 4.5 billion years ago, a Mars-sized planet named Theia is thought to have collided with Earth. It was a violent encounter that melted part of Earth's mantle and led to the formation of the Moon. Perhaps Theia also brought some water with it. And finally, Earth could have generated its own water. Chemistry says that hydrogen could react with molten rock in vast magma oceans to produce seas and oceans. It's also possible that all these ideas are true, and Earth's water came from several sources. It complicates our research, but shows how dynamic water can be in space. Before an earthquake shakes the ground, something sneaky might happen first. A slow, quiet movement with no shaking at all. No one is aware that right under their feet, the land is preparing to tremble violently, wreaking havoc, bringing destruction and devastation. A new study shows that such a slow creep might be how earthquakes begin. To figure this out, scientists didn't start with giant pieces of the Earth. Instead, they went into a lab and used clear plastic sheets called plexiglass. They pushed 2 sheets of plexiglass sideways against each other, just like how tectonic plates, huge chunks of Earth's crust, push against each other underground. As they pushed, the plastic cracked, kind of like what the Earth does during an earthquake. And even though it was plastic and not rock, the physics, the way things break and move, was the same. Earthquakes happen when 2 tectonic plates try to slide past each other, but they get stuck. The edges between them don't move easily because of something called friction. It's kind of like when your shoes grip the ground. Over time, the plates keep trying to move and stress builds up. Think of it like bending a stick. At first, it doesn't break, but if you keep pushing, it will eventually snap. The spot where the plates are stuck is called a fault, and there's a thin brittle part in that fault. By brittle, I mean that it doesn't bend, it just breaks. Here's how it happens. First, a tiny crack forms. It's small and moves slowly. There's no shaking yet, but something is already happening under the surface. The crack spreads, building up more energy. When it finally reaches the edge of the brittle zone, boom! It speeds up, suddenly racing forward really fast, almost as fast as sound. And that's when the Earth starts to shake. So scientists decided to find out how that very first crack starts. They conducted their experiment, whose setup was similar to a type of fault in the real world called a strike-slip fault, like the San Andreas Fault in California. Even though the materials, plastic versus rock, are different, the way cracks form and move is exactly the same. The experiment has helped scientists understand that earthquakes don't always start suddenly. Sometimes there's a slow, quiet start, like a warning sign before the big quake. This early stage of an earthquake is called a nucleation front. It's like a seed of a crack, gently creeping through the material long before any actual rupture happens. This quiet and slow movement doesn't release energy into the surroundings. At first, scientists thought of cracks as simple one-dimensional lines, like a straight tear in paper. But something didn't add up. The slow-moving nucleation front wasn't behaving like a normal fast-moving crack, and it wasn't clear why or how it suddenly sped up and became an earthquake. The answer came when scientists realized they had to think in 2 dimensions instead of 1. Instead of imagining the crack as just a fine line, they began to think of it as a patch, like a growing circle, that starts at the surface where 2 materials touch. As this patch spreads out, more material along its edge has to break. The important thing here is that the energy needed to break the material is related to how long the patch's edge or perimeter becomes. The bigger the perimeter, the more energy it takes to keep breaking. That's why this patch moves slowly at first. It doesn't yet cause the violent shaking we associate with an earthquake. Because it moves without sending shaking waves, this stage is called aseismic. Eventually, the growing crack patch spreads beyond the special brittle zone, where the materials are stuck. Outside this zone, the energy needed to keep breaking the material doesn't increase anymore. Instead, there's now extra energy building up, more than what's needed to keep the crack growing slowly. This extra energy doesn't stay quiet. It suddenly powers the crack to move much faster, turning it into a full-speed rupture. That's the moment when the earthquake begins and the ground starts to shake. These findings help explain how earthquakes might start off slow and silent before quickly turning dangerous. They show that small, slow cracks can suddenly transform into powerful, fast-moving ruptures if the conditions are right. Scientists believe that they can learn to detect the aseismic stage before a crack speeds up. It might one day be possible to predict earthquakes, or at least understand the warning signs better. Now, even though earthquakes are only the 3rd most common type of natural disaster, they cause the highest number of fatalities. NASA plays an important role in studying earthquakes by using satellites that orbit the Earth. These satellites collect data and images that show how the ground changes after an earthquake. For example, They can detect when the land shifts, rises, sinks, or cracks. These surface changes help scientists learn more about the strength and impact of earthquakes. NASA's satellites can also track changes in nighttime lights. If a city goes dark after a quake, that's a clear sign that the area may have lost power and could need help. Now, how about we talk about the most common earthquake myths, like the one about megaquakes? Some people really worry about super huge earthquakes, but there's a limit to how big they can get. The size of an earthquake depends on the size of the fault where it happens. A longer and deeper fault can cause a bigger earthquake. For example, the San Andreas Fault in California is long, about 800 miles, but not very deep, around 10 to 12 miles. This makes earthquakes bigger than magnitude 8.3 on that fault very unlikely. The biggest earthquake ever recorded happened in Chile in 1960. It had a magnitude of 9.5 and occurred on a huge fault that was almost 1,000 miles long and 150 miles wide. Technically, there's no set limit on the magnitude scale, but an earthquake bigger than magnitude 12 would need a fault larger than Earth, which just isn't possible. Now, earthquakes can happen near the surface or deep underground. Most occur in Earth's crust or upper mantle, down to about 500 miles deep. But the deepest ones happen only at subduction zones, places where one part of Earth's crust slides under another. In California, almost all earthquakes happen in the top 15 miles of the crust. One exception is the Cascadia subduction zone in Northern California, which continues up through Oregon, Washington, and Canada. Another misconception is that the ground can open during an earthquake, but usually that only happens in movies. A giant crack opening and swallowing things up during an earthquake is just fiction. In real life, the ground on either side of a fault slides past each other. It doesn't pull apart or open wide. Small cracks or holes can happen during landslides or ground failures, but not along the actual fault line itself. Faults don't open up because if they did, there'd be no friction, and without friction, there wouldn't be an earthquake at all. Now, some people think California could break off and sink into the ocean during an earthquake, but that's not how it happens. The ocean floor is just lower land with water above it. California can't fall in. What's really happening is that southwestern California is slowly sliding north toward Alaska along the San Andreas Fault. The Pacific Plate, which California sits on, is moving about 2 inches per year, about as fast as your fingernails grow. So, in about 15 million years, Los Angeles and San Francisco could be neighbors. And in 70 million years, Los Angeles might be sitting near Alaska. I can't wait. People often wonder whether an aftershock can be bigger than the earthquake itself. Aftershocks are smaller earthquakes that happen in the same area after a larger one. They're like our planet's way of settling down after the main shock. But if an aftershock turns out to be bigger than the first earthquake, then we call the bigger one the main shock, and the earlier one becomes a foreshock. About 5 to 10% of earthquakes in California are followed by a stronger one within a week. It's also possible for 2 quakes in the same area to be about the same size. However, very large earthquakes are rare, so it's even rarer to see 2 huge ones happen close together. So listen up. One day our sun will cool down and turn into a white dwarf. But this is not the worst thing for Earth. Before the star cools down, it will grow to an incredible size and arrange Ragnarok for us. Now, in case you don't know, Ragnarok is the fire apocalypse from Nordic mythology. So our star will burn down absolutely everything on our planet. But hey, don't worry, there's good news. This one day will come in 5 to 7 billion years. The bad news, though, is that almost all complex life on Earth will become extinct much sooner, maybe in 250 million years. But there's a small chance that our planet will be ruled by octopuses. Yeah, I know, this is too much news for the first few seconds. So let me break it all down for you, one thing at a time. We all hear about people destroying nature and polluting our planet. This is all true, but even without our intervention, the vast majority of living creatures on the planet will disappear, including ourselves. The reason is natural disasters and weather change. It sounds terrible, but it's not new to Earth. Scientists have found out that there have already been 5 mass extinctions. The last one happened about 65 million years ago, when dinosaurs disappeared. But life won anyway and took on many different forms. The 6th apocalypse may occur within the next 250 million years. Conditions on Earth at this time will be unsuitable for mammals because the level of carbon dioxide will be twice as high. This will happen because the sun will release 2.5% more radiation and it'll get too hot on Earth. The temperature in most parts of the planet will reach between 104 to 158 degrees Fahrenheit, and the entire land will turn into one supercontinent. In regions with high humidity, the temperature will be even higher, and of course, under such conditions, it will be difficult for people to walk in the park and play frisbee with dogs. No one will play with anyone at all. Let's hope we'll have colonized other planets by this time. Increasing solar fluxes will lead to a sharp loss of oxygen in the atmosphere. This means that in about 1 billion years, our Earth will look like the lifeless place it was about 2.5 billion years ago. That is, before the Great Oxidation Event. At that time, the air was filled with methane, carbon dioxide, and other gases, and the planet was inhabited by the simplest bacteria. Some of them learned how to make oxygen from sunlight and carbon dioxide. Throughout billions of years, they made so much oxygen that it became enough for the birth of new, more complex forms of life. And it seems we will return to these prehistoric times. Now, humans can't exist in such conditions, but some complex life forms hiding in the dark depths of the ocean might be able to adapt to the changed atmosphere and become the masters of Earth. These complex life forms are octopuses. There are many species of these animals. Some live in coastal areas, while others dwell in the deep waters of seas and oceans. And some species may be able to survive and create a new civilization. But why octopuses? Because they're some of the most intelligent creatures on Earth, and probably the most intelligent creatures among all the inhabitants of the dark depths. Octopuses can use surrounding objects as tools. For example, they can wear a coconut shell for protection or shelter. In laboratories, they've used various objects to complete mazes. These animals often escape from their water tanks to visit octopuses in nearby tanks. Yes, they have high intelligence, but not in the human sense. Their intelligence is more like a computer. You see, octopuses have neurons not only inside their brains, but also inside their 8 tentacles and large eyes. It's like a big data center, and their limbs sense the environment in exceptional detail, as if they were the brain. Not only their intelligence, but also their physiological properties might help the octopus survive if the apocalypse strikes. Its body has no skeleton. It can squeeze through any hole, slip past any obstacle, and their 8 highly developed limbs allow them to intelligently interact with their surroundings. Crows can bend pieces of wire with their beaks. They can throw stones into the water to raise the water level and get food. But they only have one beak. An octopus with its tentacles has at least 8 times more possibilities. They don't have spines, so they'll most likely build a civilization not on land but underwater, where it's much more convenient to move with such a body. To build a civilization, they'll need to find cheap energy. For example, hydrothermal underwater springs or tides in coastal areas. This will be a difficult task, but it won't be the most challenging thing for creating cities. It's very difficult for them to maintain social connections. By their nature, they are loners, who usually form groups of several individuals. But this is not enough to carry out large-scale construction of underwater urban areas. Parents pass on culture, history, upbringing, and moral guidelines to their children. They spend a lot of time and effort on education. Octopuses don't do this at all. The female octopus passes away shortly after laying eggs. The male octopus has only one mating relationship in its entire life and passes away shortly after the female is fertilized. So, in a sense, octopus cubs are born orphans. It's not surprising that it's difficult for them to build social connections. Over the past 50 to 100 million years, octopuses have not developed a collective feeling, and it's difficult to imagine that it will suddenly appear in the future. Perhaps something will encourage them. Who knows? Some scientists who study octopuses have noticed that over the past 10 years, some octopus species have shown certain social skills. Some live in groups of 10 or more individuals. If humanity doesn't ruin the lives of these animals by fishing and dumping garbage into the ocean, then they have a good chance of succeeding in conquering the planet. But if they fail, then the next candidates might be nematodes, those little white worms. Well, let's hope octopuses win. They seem cuter. They also may achieve a technological breakthrough much faster than we think, because when you have 8 arms, you work much better. Imagine these octopuses leaving Earth and flying to another galaxy, where they meet us humans. Do you think we could become friends? So let's say octopuses become a highly developed civilization that builds cities in the oceans. But they, just like humans, will have to think about colonizing other planets because of the upcoming Ragnarok. The sun keeps heating up and getting bigger, don't forget. Our star is currently in the most stable phase of its life. It has been in this phase for the last 4.5 billion years. But after another 5 billion years or so, the hydrogen in its core will start running out, and then the fun will begin. As hydrogen fusion slows, the core begins to contract. As the core gets smaller, it heats up until it can kick off another round of nuclear reactions, fusing helium into heavier elements such as carbon, nitrogen, and oxygen. Eventually, the sun will turn red and be so gigantic that it will swallow up Mercury, Venus, and possibly Earth. So, it may be Ragnarok not only for our planet, but for the whole solar system. No matter how tough octopuses are, they won't survive such a disaster. Earth is likely to burn down completely. Maybe it'll look like the moon, or it'll completely disappear. What will happen to the sun next? Its energy will run out sooner or later. Then it will shrink to the size of Earth and turn into a white dwarf. When a star goes out, it ejects a huge amount of gas and dust. Only the cooling core remains. All those outer layers will be floating in space, forming a beautiful nebula, and our solar system will become unrecognizable. Well, in some ways, it can sound pretty sad and scary, but hey, look at the bright side. Yeah, pun intended. It's going to happen in 5 to 7 billion years, so relax. Humanity has been living on Earth for about 40,000 years. If we compress the entire history of our planet into one 24-hour day, then the history of people will be equal to 1 second. If we achieve such a development in 40,000 years, what'll happen in 100,000 years, in 1,000,000 years, in 1,000,000,000 years? It's hard to predict. So how about going to the park and enjoying the sun at its best? Bring some sunscreen.
Something is about to reshape the entire future of the West Coast. The coastline, the infrastructure, the whole map. Scientists fear there is not one but 2 big earthquakes coming, one caused by another. This wasn't even on the radar for most people, but new research is changing everything. For decades, everyone treated the San Andreas Fault and the Cascadia Subduction Zone like 2 separate monsters that just happened to live in the same neighborhood. They were powerful, yes, but independent. But now, scientists believe these 2 giant faults are mechanically linked, and one can literally pull the other into rupturing shortly afterward. Cascadia moves, San Andreas moves. San Andreas tears, Cascadia tears. And the potential consequences of that are honestly haunting. Scientists found evidence that it happened at least 10 times in the last 3,100 years. Earthquake, pause, earthquake. It comes from marine sediment cores, which are like time capsules pulled up from the ocean floor. Researchers analyzed layer after layer of seabed sediment and found doublets. Paired debris layers created by 2 massive quakes happening so close together that the ocean barely had time to settle between them. That discovery takes us to the Mendocino Triple Junction, the geological troublemaker of the West Coast. It's the place where 3 tectonic plates crash and grind into each other like badly aligned gears. It's also the zone where the San Andreas meets Cascadia. which makes it the perfect place for these double quakes to form. The stress changes caused by a rupture in one fault travel straight through this junction and destabilize the other. It's benign when it happens to a bookshelf. When you move one book, 3 others shift. But when you think about it like a coastline with millions of people, entire cities, major infrastructure, it instantly feels terrifying. To many people who live on the West Coast, the San Andreas kind of feels like a California's problem, and Cascadia like an Oregon and Washington's problem. But when you understand that these two faults can essentially fire at each other, it stops being a local issue and becomes a continental one. A Cascadia megaquake alone can hit magnitude 9.0 plus, rip open 600 to 700 miles of seafloor, and send a tsunami roaring toward the Pacific coast. And it could just be the first quake, and then, maybe minutes later, the San Andreas snaps in Northern California. The shaking could ripple down the state like a zipper tearing open a jacket, and if it goes the other direction, it could be just as bad. If the San Andreas ruptures first, the intense stress redistribution can destabilize the Cascadia subduction zone. You could get the California quake first with buildings rocking, highways breaking, and power stations failing. And then, soon after, the ocean pulls back in Oregon or Washington. And the 20-minute countdown to a tsunami begins, a follow-up disaster. It's the kind of chain reaction you don't want even in a video game, let alone real life. This discovery also tells us something eerie about the earthquake in 1700, the one that sent a tsunami across the Pacific so huge that it struck Japan with no warning. Japanese fishermen called that wave the orphan tsunami because it arrived without any felt shaking. Only centuries later, scientists figured out that it came from the Pacific Northwest. But until recently, no one knew that the San Andreas might have felt that event too, and it possibly slipped or destabilized because of it. So, the whole West Coast may have moved together. And we've come to the scariest part. All this isn't about if, it's strictly about when. The faults have a rhythm, a pace, and a geological heartbeat. We've seen how they behave across thousands of years. We know what they did, and now we know they sometimes do it in sequence. The real fear isn't the first quake. California already expects a big one. The real fear is the second quake, the one that comes before you've checked on your family, before emergency responders regroup, before the power comes back, and before the dust settles. Even if you don't live on the West Coast, this matters for you too. The ports in California, Oregon, and Washington handle a massive chunk of America's imports. Knock them offline, and it's not just the coastline that feels it. The ripple hits the entire country and potentially the world. Grocery prices spike, supply chains freeze, gas availability dips, shipping timelines go nuts. The world is much more connected than any of us thought, and a geological double punch on the Pacific coast wouldn't stay a local disaster. It would spread, thread by thread, into everyone's life. So, those in power must prepare not for one giant rupture, but for two. Emergency plans, evacuation routes, response times, and power grid designs, all of it needs updating. Because nature has now shown us what even a single major rupture can do to a modern economy. It happened in Japan in 1995, on January 17th at 5:46 in the morning. The quake hit right by the northern tip of Awaji Island, only 12 miles from Kobe, a huge, busy city with about 1.4 million people back then, and another 2.6 million in Osaka nearby. The rupture ripped along the Nojima Fault for about 25 miles. That doesn't sound like much until you realize entire buildings can't survive that kind of sideways shove. More than 5,000 people lost their lives. 43,000 were injured. Nearly 400,000 buildings were irreparably damaged. This disaster hit one of Japan's largest industrial zones. And when you mess with a place like that, the shock doesn't stop at the shoreline. The damage was $200 billion US in losses, from smashed buildings and infrastructure and many businesses shutting down. Kobe's port just collapsed. Only 30% of the Osaka-Kobe railway lines worked. part of National Route 28 literally vanished into the ground. Schools, hospitals, and municipal buildings, 85% of them took damage or were unusable. Fires broke out across Kobe, almost 300 separate incidents, burning the equivalent of 70 US city blocks and taking another 600 to 700 lives. Almost 100,000 people permanently left the region, 2.5% of the whole population gone in less than a year. And here's a detail that stuck with me. So many bridges failed that engineers suddenly had to confront how poorly older designs handled lateral shaking. Houses with heavy tiled roofs, built to fight typhoons, crumbled because all that weight sat too high. But the newer homes made after the 1981 building code revision stood. And that's when Japan realized that modern seismic standards were crucial to follow. Japan threw $58 billion US into restoring the region. Power came back in days. Roads and rail returned in 5 to 8 months. The main expressway took 21 months. The port was fully rebuilt in just over 2 years. And by then, all debris was cleared. Within 15 months, manufacturing jumped back to 98% of its old level. Stores reopened. By 1999, Kobe's economy reached roughly 75 to 90% of pre-quake levels. Japan overhauled its disaster management system entirely. They set up the Central Disaster Management Council and rewrote building codes. They upgraded everything from emergency drills to fire-resistant city layouts, and they launched the Earthquake Early Warning System that now gives Japan those precious few seconds before shaking hits. The same system that saved countless lives since 2007. But despite all this improvement, the Kansai region still sits on dangerous ground. The Roku Awajishima fault system, the same one that snapped in 1995, still runs under them. The 2018 Northern Osaka quake and the 2024 Noto Peninsula quake reminded everyone that this threat didn't disappear. It just waits its turn. A future large event on that system could hit even harder simply because the region has grown more complex, more interconnected, and more economically loaded. So Kobe wasn't even a triggered double fault rupture, but it still broke a major industrial hub, reshaped a national economy, and permanently changed global shipping routes. That's why when scientists started talking about 2 joint faults firing off back-to-back in Cascadia and San Andreas, you don't even have to imagine the consequences. We already got a preview in 1995.